Okay, so we'll finish up 2.1, then we'll get into 2.2. As we get into 2.2, the topic's going to be what is this inverse matrix thing, how can we find it, and when does it actually exist? And as I talked about last time, we'll do a chapter 1 quiz at the end of class today. All right, so transport's properties. We're pretty much going to list these things. We're going to start with the left-hand side and just kind of write out our intuitive guess to the right-hand side. If I take A and I transpose it, if I flip the rows and columns, and I transpose it again, flip the rows and columns again, where am I going to end up?
Where you started.
Back to where I started, absolutely. So I'm going to be left with A. So the transpose of a transpose is back to the matrix we started with. What about the transpose of a sum? A plus B, that quantity transposed. What's going to happen here?
A transpose plus B transpose.
Absolutely. Now that just looks right? That seems to make sense. Remember, we should kind of try to think through it a little bit. If I wanted to prove this, it's really just a matter of collecting terms. It's writing some A, it's writing some B. It's saying what happens when I actually do the addition. Well, I get the A term plus the B term here, the A term plus the B term here. If I were to transpose this thing, I'd just be switching these two values around. But if I transpose the individual pieces, I'd be switching these values, and then adding them. So of course they'd end up in the same position. Okay, so if you really want to kind of dive into it a little more, you just write out the matrix in kind of general terms and just think about what the process that happens. All right, R times A transpose is the same thing as R times A transpose. Right, when we multiply a matrix by a scalar, we multiply all the terms, so it doesn't really matter when we transpose it. All the terms have that factor of R in it. We just talked about the product. In the product, we can transpose the individual matrices, then we have to reverse the order of the multiplication. And the last one, identity. Identity transposes what? Just identity. And what is identity? It's just a diagonal matrix with just ones on the diagonal. So all these zeros are just switching places with all those other zeros. All right, any questions about the properties? All right. All right, so then at the end of class, we're talking about these warnings. We talked about the properties of matrix multiplication, and the big issue was it wasn't commutative. And so with that comes a couple other warnings we have to talk about. So the first one was that it's not commutative, so we can't just switch the order of the multiplication. The next one was that AB equals AC does not necessarily mean that B equals C. From the set of real numbers, we're used to this idea. We're used to kind of doing it automatically as we solve equations. We can't do that with matrices. The next one is also an important one. A times B, if A times B equals 0, that does not necessarily mean that A equals 0 or B equals 0. So this is the fundamental theorem of algebra, actually, but it doesn't apply to linear algebra with matrices. So of course the big question is why not? We talked very fast through this last time, but the big idea here is that we don't have a sense of division yet. We have a sense of multiplication, but not division. If I wanted to show for real numbers that AB equals AC implies B equals C, I'm really just dividing both sides by A. I should be all set. Well, what does it mean to divide something? What is division? So once again, last time we went through this pretty quickly, so I really do want to recap it just to make sure we're happy with the idea. If I have 3x equals 6, I want to solve that equation, we just divide both sides by 3. So really what we're doing is we say, because we're working with real numbers, we have a property of real numbers said that there exists, we can say for every value in the real numbers, for every real number, there exists some other thing like this, some inverse value, such that x inverse times x is going to give me 1. I have this inverse thing. And for real numbers, what is the inverse? What is the multiplicative inverse of 3, for instance? A third, absolutely. All right, so for real numbers, this inverse thing That raised to the negative 1 just means I'm calling it the inverse. But for real numbers, this means 1 over x. So really what I do here is I multiply both sides by a third. And then by the definition of the multiplicative inverse, this is 1 times x equals 2. I say, well, 1 times x is 1. That's another property. And then I get down to my equation. That's really what we're doing here. So the question now is, do we have that same thing for matrices? Do we have an inverse matrix so that I can just say A inverse times A equals identity? And the answer is sometimes. So in other words, only for certain A. For certain A, we can write out this inverse thing. And that's what we're going to talk about in this next section. So 2.2 and a little bit of 2.3 is all about the inverse of a matrix. We're going to learn how to compute the inverse matrix. We're going to talk about its properties, its characteristics. Then we're going to talk about when it actually does exist. We now know that it doesn't always exist. At the end of class, we'll talk about how we can tell whether it exists or not. But first, let's just do some calculations. Let's just calculate some of these. All right, so we're going to start by calculating a small one. We're going to start by calculating the inverse for a 2 by 2 matrix. This is a very specific matrix. It's a 2 by 2, and so we have kind of a specific formula for it. So the inverse of a 2 by 2 is 1 over the determinant. We're going to say what that determinant is here in a second, but it's going to be some number value, times this new matrix. And how did I get this new matrix? All I did was flip the diagonal values, flip the A and D, and I changed the sign of the off diagonal. And you're going to use this enough where you're just going to want to have this one memorized. You want to have the formula for the inverse of a 2 by 2 memorized. We'll show you a process so you can generate this later. That's a good one just to have down. So it's 1 over the determinant, and the determinant we're calling the product AD minus BC. It's this product, A times D, minus C times B. And you've probably heard of that before for this. This is how we calculate the cross product, for instance. We write out a fancy determinant thing, and we calculate these little mini determinants. So you've probably seen this calculation before. And we're going to talk more about the determinant in general in chapter 4, I believe. So right now, we'll just have this as the definition for a determinant of a 2 by 2. So let's calculate the inverse of this matrix. I have 1 over the determinant. That's 1 times 4 minus 2 times 3 times the matrix where I flip the strong diagonal. I change the signs of the off diagonal. And that's it. And now I just simplify. I have 4 minus 6 is a negative 2, so this is negative 1/2 times that matrix. And if I have a scalar times a matrix, I can just multiply all the terms by that. So here I'm going to have negative 2, positive 1, positive 3/2, and negative 1/2. And this is supposed to be A inverse. Any questions? Did I do it right? Did I make any mistakes? How can I check? That's a good way to check to see if it's really inverse. Absolutely. What is the inverse matrix? The inverse matrix is some matrix, that's just the notation for it, that if I take that matrix times A, I should get back to identity. I should also be able to take A times A inverse on the other side and get back to identity. This is really the definition of the inverse. It's some matrix that I can do that to. That's true. So when I calculated this piece, that should hold. So I should be able to take A, which is this thing, times my inverse matrix, and I should get back to identity. So we'll chug this thing out real quick. This will give me negative 2 plus 3, negative 6 plus 6, 1 minus 1, and 3 minus 2. Which sure enough simplifies to 1, 0, 0, 1. And really I should check it the other direction as well, but I'm pretty happy at this point. Any questions? Once again, your calculator, I'm sure, will have an inverse matrix button. Right? But if you have to do this on the exam, you have to show your work. Any questions with the calculation? All right, your turn. So for now, just find the inverse of this thing. Actually, you know what? Let's do this one together because that's the same matrix, right? Yeah. All right, so let's see what we do with this thing first. So now we have a matrix, and I have a b value, and I want to use that thing to solve this equation. This is one of the big tools of the inverse matrix. So the idea is if I have ax equals b, if I had 3x equals 6, I want to divide by 3. I want to multiply both sides by the inverse. Well, that's what I want to do here. I want to left multiply, because remember the side matters here, by my inverse matrix. So I'm multiplying on the left of each side by my inverse. And of course, the reason to do that is because A inverse times A is what? Identity. And over here I have A inverse B. And identity times X is just X. So my solution should be A inverse times B. So now I can do this without the row reduction, without the augmented matrix, all that kind of stuff. Once I have the inverse, I just take the inverse times b, and that should give me my solution. So if we grab that inverse from up here, our inverse was negative 2, 1, 3 halves, negative 1 half. That thing times 1, 1 should give me my solution. Now I can just calculate my solution directly. This is negative 2 plus 1, and 3 halves minus 1 half. This is negative 1, 1. All right, any questions about that? Of course, in mathematics, we can check that real quick. So now the warm-up. That was warm-up. All right, so there's my matrix. I'm defining it to be A. I can calculate the inverse to make sure that's correct. Sure enough, that's what we had before. And then one quick note here. I can type A raised to the negative 1. But if I actually evaluate that, that turns out to be a different value. So a to the negative 1 in mathematics is not the inverse. That's a different operation. When you write a to the negative 1, it's going to take the reciprocal of all the components. And sometimes that's a useful thing too. So we use a to the negative 1 to mean the inverse matrix, but if you just type it in here, it's going to do a different operation. So in mathematics, if you want the inverse, you have to type inverse of that matrix. So inverse command of A. Okay? But now if we have that inverse, I can take that inverse dotted with whatever that B value was. And sure enough, that should give me my solution. So we can do these real quick in Mathematica. I'm sure you can do them in your calculator as well. And also real quick, because I forgot to show this for the warm-up here, just to make sure that we know how to do this stuff. So I'll take the transpose of a matrix. The easiest way to do that is to hit escape, TR, escape. There's also a full command called transpose you can use, but escape, TR, escape is really kind of the fast way to do it. If I want to show the nice way, I would do matrix form as well. And there's the transpose of B. So escape, TR, escape is a nice way to get a transpose real quick. All right. So now we've done that multiplication. Now you can try one on your own here. So given this new A and this other B, find that inverse matrix, and then use it to solve that equation, that matrix equation. Solution, check your neighbor. Differences, combat. One, three, and 1/2. Got that. Matrix A is 1, 3, 1/2. Alright, so I've done mine. From?
How did you get 2?
Stu or this?
No, but the top. Big one.
So,
Yes.
over here, so I have 1 over the determinant.
Okay.
I have my strong diagonal product, 1 times 2 minus 3 times 1/2. This difference is 1/2. And I have 1 over 1/2. So instead of dividing by a fraction, I can flip it and multiply. So 1 over 1/2 is the same thing as dividing by, or multiplying by 2. I have 1 over 1/2. Same thing as multiplying by the reciprocal denominator. Other questions? Good questions. Make sure you ask questions if you have them. All right, those little things can be annoying later. So make sure you get your questions answered. Any other questions? Okay, so that's great. That's for 2 by 2s. But what about bigger matrices? How do we find those inverses? Well, we actually have another process. What we do is we set up a special augmented matrix where we have our matrix on the left-hand side and we augment it with the identity matrix of the same size as A. All right, so we set up an augmented matrix that looks like that. A on the left, identity on the right. And then all we do is row reduce this thing. We do a full reduced row echelon form, And when we're all done, it will end up to look like this. We're going to turn the A side into identity, and whatever we get left on the other side, that's going to be the inverse. So we just worked with this matrix. To use this process, all I do is set up the augmented matrix 1, 3, 1/2, 2, augmented by identity. A on the left, identity on the right. And then we row reduce it. So if I want to row reduce, the first thing I'm going to do is take R2 is equal to R2 minus 1/2 R1. Right, I want to get rid of the 1/2. So I'll take 1/2 minus 1/2 of the first row. First row stays the same. Oops. I have 1/2 minus 1/2 is 0. 2 minus 1/2 of 3. So that's 2 minus 3/2. 2 minus 3/2 is 1/2. 0 minus 1/2 times 1, that's minus 1/2. And 1 minus 1/2 of 0 is 1. What am I going to do next? What's my next operation?
Multiply the second row by 2.
Yep, multiply the second row by 2. Right, I've eliminated this value. Now I have to turn this one into a 1. So I take the second row, I multiply it by 2. Oops, that's a 3. I get 0, 1, negative 1, 2. And then my next step should be to take row 1 and replace it with R1 minus 3 times R2. I'm going to eliminate this term right here. Now the second row stays the same. I get 0, 1, 1 minus 3 times negative 1. That should be 4. Okay. And 0 minus 3 times negative 2 should be negative 6. And does that look like my inverse matrix? It does. Well, so now this is identity and this is my inverse. And of course the nice thing is this can work with larger matrices as well. So if this was a 3 by 3 or a 4 by 4 or larger, this process would work. All right, any questions about this process? We're going to go through a little bit of why this works in a little bit. So right now it's a process that we can go through to find the inverse. But now there's kind of another question that you might bring up at this point. And we've been solving AX equals B already. We've already solved this thing. How did we go about solving this in the past?
Did augmented matrix, row reduce it.
Absolutely. We made an augmented matrix and we row reduce. And now we know, oh, we can just solve this using an inverse. But to find the inverse, we're forming an augmented matrix and row reducing. So are these both valuable? Is one better than the other? Well, one way to think about this and to actually use this is to think about how you would actually calculate this thing. All right, so now I'm in Mathematica, and I want to do a little bit larger matrices. So these first two commands are generating some large matrices. I'll generate some small ones first so we can kind of take a look at them. What this says is make a matrix A and take a random integer between the ranges of 1 and 100, and you're going to take 2 by 2 matrix of these things. So when I run this thing, let me delete the semicolon so we can see it. There is my A. It picked out 4 random values. And it made a 2 by 2 matrix of random numbers between 1 and 100. But if I want to make a large kind of random matrix, I can do that. So now I have A and B. And so now basically I'm going to solve my system, AX equals B, 2 different ways. The first way, I'm going to solve it by calculating the inverse matrix. and multiplying it by b. And I'm going to store that solution to solution 1. And the nice thing about Mathematica is I'm going to take a little timing thing to see how long that process takes. So by calculating the inverse and using that to solve this equation, it's going to solve it and take 0.43 seconds. Not too bad. But now what I'm going to do is I'm going to use a different command called linear solve. What this command is essentially doing is doing a row reduction. It's putting A on the left, B on the right, and just doing a row reduction process to try to solve it that way. Wow, that's a lot faster. Okay. In general, doing a row reduction is a much faster technique. So anytime we really solve a system like that, we're really not finding an inverse matrix. We're almost always doing a row reduction computationally because it's that much faster. Now, of course, we want to make sure that we're getting the same answer here. So all I've done here is subtract those two values. If I take solution 1 and subtract solution 2, what should I get? A whole bunch of zeros. All right, so I really am getting the same result here, just much faster way. So why would we ever calculate the inverse then? What's the point? There's really two different points. One is because the inverse is an important conceptual tool. As we generate formulas for things later on, or we generate theory, we're going to want to use the inverse in our calculations. We do some sort of algebraic approach to make some new proof. We know that an inverse exists, we can show it exists, and now we want to have a notation for it. So basically we need to show that it exists and then use it throughout some sort of proof process. That's a very important piece of the inverse. But it's also useful in practice as well, because we just showed that it was much faster to solve using linear solve, but that's with a specific b. What if I have a whole bunch of different b's? What if A is some sort of fixed, constant process, and it's b that's changing? We want to find the solution for a whole bunch of different b's. That happens a lot of times. In section 1.10, they talk about a difference equations model where they have a matrix that represents like population growth for a city. And so you take your current population as a vector, and then you multiply by this matrix, and you'll get the population another year from now. But there's other processes like that where we might have some sort of output b that's changing. We want to find the solution when b is this. Okay, well now we want to find the solution when b is this. Well, if we want to do that and a essentially stays the same, what we can do is calculate the inverse once, and that might take a little bit of time. But then once it's calculated, all we have to do is take that product. And if I find out how long it takes to do that product, it's even faster than doing the linear solve. So I invest some initial time to calculate the inverse, but now every single time I use it after that, I'm saving some more time. So that's one way in which you'd use the inverse, even though it's a little bit of a slower technique. Okay, any questions about that? There's really two sides of linear algebra. Here's how we're going to do it in class, and that's how you really apply it in real life. The computational side of linear algebra is a complicated tool. We start talking about how the computer stores values and actually does the calculations. They're very interesting as well. Okay, any questions about that? Okay, so let's talk more about why this process works. Okay, row operations can be thought of as multiplication by special matrices called elementary matrices. Elementary matrices. To form these elementary matrices, all we do is kind of do the desired row operation to the identity matrix. That's a lot of words. What does that actually mean? I have this matrix, A, B, C, D. I want to do a row operation to it. One row operation might be doubling the first row. So I can double the first row, but now for every operation I have, I can think about it as instead by taking this matrix and multiplying it by a certain matrix. This is an elementary matrix. All I did was take the identity and double the first row of identity. And when I do that multiplication, and I actually work it out, this is the matrix I get. And it looks like I just doubled that first row. So for every one of our row operations, there's an associated elementary matrix. So for example, I have a matrix. Everybody see that? Is that big enough in the back? I have a matrix. If I take this product, what am I going to get? Let's call that matrix on the right A. Is anything going to happen to A? No, because I'm just multiplying it by identity, right? If I were to take identity and change it like this, how is that going to affect my matrix A?
Double the values in the second one.
Sure enough, there it goes. I doubled the values in the second row. Because I doubled the values in the second row of the identity matrix. Now, what if I want to do a different row operation? What if I want to take the second row and add the first row to it? Well, I just do the same thing for identity. I take the second row and add the first row to it. Now, what do I get? What is row 2? It's just the sum of this row plus this row. What if I wanted to add 2 times row 1? It would just be this thing. So this is what I mean by every row operation you can think of as just multiplication by an elementary matrix. Any questions about that? There's a whole bunch of special properties about the elementary matrices. For instance, every elementary matrix is invertible. We can always find an inverse. And that makes sense because you can think of any one of those row operations as also having inverse. All right, what's the opposite of doubling a row? Multiplying a row by 1/2. So every operation we can go backwards on it as well. Now one thing to note though is we have to be a little bit careful. Here I am left multiplying, and that's actually important. If I were to right multiply by these elementary row operations, let's make kind of a nice one here. Before, this would have doubled the first row. Now what did it do? It doubled the first column. So when you multiply on the right, it's doing a column operation. When you multiply on the left, it's doing a row operation. Okay, what does that have to do with anything? Well, when we put something in row-reduced form, all we're doing is row operations. So essentially, it's the same thing as taking this matrix and hitting it with a whole bunch of these row operations. Right? This first row operation maybe doubles the first row. This one does some, first row minus 2 times the third row, whatever we're going to do here. And so if I do a whole bunch of these, it's a process of row reducing A. Now the idea is if I can do a row reduction and get all the way to identity, remember there's different outcomes when we do a row reduction. We might get to this. We might also get to something like this. Well, it turns out for there to be an inverse, we have to get to an identity. But if we can row reduce to identity, then we can really just take the product of all these matrices, and that will turn out to be the inverse. Because think about it, if I can multiply A by this, then this, then this, then this, and then get to identity, well, I could just multiply all these by themselves, and I would get some matrix. And then I'm saying this matrix times A equals identity. Well, by definition, this is the inverse then. So this is another way we can get to inverse. Now, what are we doing when we do that augmented thing? That augmented process is just taking A and then identity like this. But when we do that multiplication of matrices, it's the same thing as saying, well, E1A and E1I. I mean, we can really just think of that as multiplying each of those vectors inside of that matrix by that other matrix. And so this process is really the same as this. And so all that identity over here is doing is just collecting all the elementary matrices. That's all we're doing here. It's like we're applying all of them to A to change A into identity. And all we do is augment with this I because this is going to collect all these values as we go. So we don't have to think about these separately and then form the inverse. This is just going to gather them all up. Because what is I times E1? Just E1. So this really doesn't change anything. It's just saying, okay, E1, and then E2, then E3, E4. This is just gathering up all these values. Okay, so that's why that process of row reduction works. Okay, this is going to bring us to two things now. Extra credits. I'm going to post these on Canvas later today as assignments. They're optional. Extra credit in this class is going to work like this. I'm going to lock out 2% of the grade. So this course is going to be total out of 102%. That 2% is going to be based on this extra credit. So if you do all the extra credits and you get full point, it's like a 2% bump to your grade. Okay. Now I do this for a couple reasons. One, because I think this information is pretty useful and it's a good thing to kind of investigate. But also, there's always borderline cases at the end of the semester. And so this is a way for you to take control of your own borderline case. Right? So at the end of the semester, you're 0.3 away. You didn't do any of the extra credits. Don't come begging for that 0.3. Because I'll tell you, why didn't you do the extra credits? They're not going to be challenging. Right? There's going to be two kind of flavors to them. First one says, row reduction is also known as Gaussian elimination. Why? Well, there's some guy named Gauss. All right, so the first extra credit, we do a one-page bio on why it's called Gaussian elimination, who this Gauss guy is, and anything else you find interesting when you read about it. It doesn't have to be cited. If you want to send me the link to the website you used, right, feel free to use Wikipedia. That's fine. Right, this isn't a formal thing here. It's just for you to kind of look into the background a little bit. Right, so just do a little bit of reading, throw together a little paper, one page, quick bio, anything you find interesting about Gauss or Gaussian elimination. Well, the next one is maybe a little more involved. It's a mathematical one. We just said that this is that process we've been doing. So I want to show that it works. So what I want you to do is make up A, choose A, some 3 by 3 or bigger, but 3 by 3 will be easiest, right? Choose some 3 by 3 and think about how you would row reduce it. Okay, so take a 3 by 3, do the row reduction, think about the steps you needed, and then find those elementary matrices that you would need to do the row reduction. Okay? So then you need to show me that, so you actually type in A, you type in these other matrices, and you can show me that this is true. Then I want you to take these matrices and just multiply them by each other, and you'll get a matrix. And then I want you to calculate inverse of A with Mathematica, and you'll get a matrix. And obviously this should be the same as this. So you're just kind of verifying that that process is true in Mathematica. So I post those two later today. Once again, they're extra credit. I will probably leave them open for 2 weeks-ish. I don't want to say use the rest of the semester because then nobody will do it to the very bitter end. So they'll be open for probably about 2 weeks or so. Yep.
Do we do one or the other?
We can do both. Yep. I'll have a couple more later in the semester. So if you want the full 2%, you got to do them all. If you do half of them, then you can possibly earn up to 1%. I tend to grade them pretty loosely. So, okay. Now we know how to calculate the inverse. So now there's some special properties of the inverse. Some there's going to be more intuitive than others. So, the inverse of an inverse. The inverse of an inverse is back to that original matrix. It's almost like that transpose property. Now we have another one. Well, if I have the inverse of a product, it's the product of the inverses, but in reversed order, just like that transpose as well. And the last one says that if A transpose is invertible, then its inverse is the inverse of A transpose. So if A transpose is invertible, then the inverse of this thing is just A inverse transposed. So those are the properties. Okay. So now what I'd like to do is just prove one of the properties. Once again, not so much because I need you to go through a formal proof, but I need you to see once what it means to prove something with an inverse. All right, because it's really just a definition of what the inverse is. Okay, so let's prove this one right here. Okay, so all this is really saying is saying that the inverse of that product is equal to this thing. It says the inverse of AB is this thing. So to show that's true, all I need to do is say, well, okay, if this thing right here, if this is the inverse of AB, then AB times that thing should get me to identity. That's it. And of course I have to do that both ways. AB times this thing and this thing times AB in the opposite order. So I have to do both orders. So that's all I'm really trying to show. So I have to do a bunch of steps to get down to identity. Now all these proofs are actually in the book. They just do them all in a line. And I'd rather do them as a stacked thing and use better justification. So we can really write out what the reason for each step is. So if I start out, I'm trying to get to identity. The first thing I'm going to do is to say, okay, that's the same thing as this. But I can't do any of these steps without a justification. So what is the justification for that step? There's a property that tells me those two things are equal. I can just move the parentheses around. Associative property. So I can do that because of the associative property of matrix multiplication. Now I did that because I really want to take B times B inverse. Because when I take that, what do I get? I get identity. Why do I get identity? There's a reason for that. It's the definition of inverse. Definition of the inverse matrix. But this is the same thing as just this. Why is that? A lot of these seem kind of trivial, right? But we actually need properties to make sure this is true. And so we should justify each one of these steps formally. This is the identity property. We have a property that says identity times a matrix is just a matrix. So this is the identity property of matrix multiplication. And then lastly, A times A inverse is what? Identity. Because why? Yes, it's the definition of the inverse matrix. And that's it. Now we go back and show that this thing multiplied on the other side of AB also gets me to identity. Pretty much doing it exactly the same way. And that would be the proof. So once again, your book does the proof of the other ones as well, and it just kind of writes out in a line, which is fine. That's how you do most of these. But once you should just see how it's written out, and we actually justify each of these steps using the properties. That's what a real clean proof looks like. Okay? All right. So we're just about done here. The last part says, when is there an inverse? And we kind of saw that. We kind of saw one justification of that already. We were able to find these elementary row operations, the elementary matrices, that would allow us to row reduce to identity. So that's one characteristic here, that we can row reduce to identity. So that means I can take A, I can do my row reduction process, and I get to this thing. When I do my row reduction process and I get to that thing, I can start talking about the pivot positions. What's special about the pivot positions here? One in each column and one in each row. Tells us a couple things. It tells us that A has to be an n by n. We only talk about inverse matrices for square matrices. If it's not square, it doesn't have an inverse. Okay? If it doesn't have an inverse, it's also known as singular. Another term for that. It's also used in the book. So one, they have to be square. Two, I have a pivot position in every row and every column. So that means if I think of this as a transformation, this transformation is what? There's a pivot position in every row and in every column. So that means it's one-to-one and onto. It's both of those things. And that's actually another nice relationship about this thing. Because we know about inverses. We know that y equals x squared. Does that have an inverse? It actually doesn't. Right? It would be plus or minus the square root. Well, it doesn't because that's y equals x squared. It doesn't have an inverse because it doesn't pass the horizontal line test. The horizontal line test says there are two different x values that bring us to the same y value. It's not one-to-one. For a function to have an inverse, it has to be one-to-one and onto. So this relates directly to that. Now that, of course, ties everything back together. Right, when is it 1-to-1 and onto? We have all these statements that are equivalent. So 2.3 says this. Here's a giant theorem. It says if the matrix is invertible, all these things are also true. I think I got them all. No, not quite. Yeah, just barely fit them on there. And it's just a recap of all the stuff we've done. Right? If it's 1-to-1 and onto, well, then the columns span that space. Then it's 1-to-1 here. Columns are linearly independent. It has n pivot positions. It has one for each column, one for each row. There's actually a whole bunch more we could add to this list if we wanted to. Okay, so check this over at 2.3. And I have my quiz here still, don't I? All right, the quiz. Hoping to give you a little bit of time to work on it. It's not really a quiz, but an exam prep. And it's a larger than exam review. What I'd like to do is let you work on it today, and then give it back, or take most of class next time to kind of finish it up. So work on it tonight, see how far you can get, and then bring it to class. We'll recap some of this stuff real quick, and we'll get in little groups, and you guys can finish hammering through this. I'm going to give it a participation kind of grade at the end. It'll be worth like 5 points, so a decent amount of points. I'm just going to walk through and make sure they're completed. I'm not going to check them for accuracies, but then at the end of class, I'll also give you a key which to study from. So this will be like a practice exam. It has a lot of stuff on it. Think of it as a practice exam. You get a good jump on it tonight. It's long, and you won't have time to do it all in class tomorrow. All right, sorry for going so late.